So, last time we defined the notion of ideal class group for a general Dedekind domain, and I told you that the ideal class group need not be finite for a general Dedekind domain, but for rings of integers of number field we are going to prove that the ideal class group is a finite group. We also saw that ideal class group is an abelian group and it measures the failure of a Dedekind domain to be a unique factorization domain or a principal ideal domain, which are the same thing for a Dedekind domain. Okay. So, today our aim is to prove that the ideal class group of a ring of integers of number fields is finite. And I told you last time what the strategy is going to be for proving such a result. So, last time we saw that for a general Dedekind domain, an ideal class always contains an integral ideal. What happens in the case of number fields is that it contains an integral ideal of a bounded norm. This bound is independent of the class, it only depends on the number field. And we also saw that there are only finitely many ideals in any given number field of a bounded norm. So, this will tell you that there are only finitely many ideal classes and hence the ideal class group is finite. Okay. So, proving any finiteness result like this requires what is called notion of a height, and we are going to define a very naive notion of height to prove finiteness of class group. This is going to give us absolutely horrible bounds to prove finiteness of class group, which are of no practical use. It is only of theoretical use that we get that the ideal class group is finite. If we want to use these bounds in to compute ideal class group, it's not going to be, it's going to be almost impossible to do so. And so, later on we will get a much better bound to prove finiteness of class group. But I just want to emphasize that this, even this naive notion of height is kind of very powerful and gives you finiteness of class group. So, it is of theoretical importance rather than of practical importance. Okay. So, let K be a number field as usual, and as usual we denote n by the degree of K over Q. So, what we are going to do is we are going to fix an integral basis of OK. So, let alpha 1 up to alpha n be a z basis of OK all right, and we are going to define our height in terms of this basis. So, let beta be any element of K. You can write beta as B1 alpha 1 and so on up to Bn alpha n for Bi's in Q, right. So, if you take a z basis of OK, it is also a Q basis of K. All right. And so, we define height, which is denoted as h of beta, to be summation mod of Bi. Okay. So, that is what height is. So, you see it kind of, it depends on the choice of integral basis in a very crucial way, and you might think that it is actually not very useful, but it turns out to be useful to prove finiteness of class group. Okay. So, here is a remark or slash exercise if you like. If so, okay, let me put it this way. So, there exist there exists a constant delta greater than 0 such that height of alpha is greater than delta for all alpha in OK minus 0. This comes is discrete in q to the n. This is one of the first results that we proved, that OK. So, when you fix a basis, a q basis of k, you can identify k with q to the n, and the image of OK in this q to the n is a discrete subset, right. So, this is going to be useful, this remark. And now here is another quantity. So, what you do is you let C be equal to the maximum of all these numbers. So, you take these finitely many numbers alpha I, alpha j, right. So, 1 less than or equal to I j less than or equal to n. So, there are n square of these numbers, you take their heights and you let C be the maximum of their heights. So, again something that is right. Okay, maybe another better way of putting this remark is as h of alpha is always in z, right. So, this is another way of putting this remark. Okay. So, when I wrote this remark, what I had in mind is that alpha i's are not necessarily an integral basis, but since I have chosen alpha 1, alpha 2 up to alpha n to be an integral basis, it is actually in z. So, that is another way of putting this remark. Anyway, so C, this is an important quantity that we are going to use in the next result. All right. So, what is the next result? This is the main technical result. So, let A be a non-zero fractional ideal in OK. So, A is also a lattice in Q to the n, right, and so the heights that each element of K takes is also a discrete set in Q to the in Q, right, and so there will be an element with minimal height. So, let alpha in A minus 0 be of minimal height, right. So, this lemma, this remark that I wrote, it applies to this fractional ideal, and perhaps that is the wording that I should have used. Okay. So, then what happens is for any beta in A, we can find gamma in OK such that, sorry, gamma in OK and M in Z such that the following thing holds. So, when you scale your right, when you and you subtract gamma, you get something of bounded height. Okay. So, you see this okay, let me finish the statement and then I will make the comment. And 0 is less than m is less than or equal to capital M, which is n times C plus 1 to the power n plus 1. Okay. All right. So, let me make the following, let me make a number of comments about this, and I am not going to write them down here, but they are very important. So, first of all these bounds C plus 1 inverse and M, they only depend on the field and the choice of the integral basis. They do not depend on the fractional ideal A. So, that is an important point. Okay. The second point is that if A were a principal ideal, principal fractional ideal, then this alpha would just be a generator of A. You can choose alpha to be a generator of A, and then if you take anything else, right, you could write it in terms of as a multiple of alpha, and such a thing would be trivial. So, we do not have, I mean, every fractional ideal is not necessarily principal. So, what this is saying is that if you take any other element, you can divide out by this element of minimal height, and you more or less get bound on the height. Well, there are some perturbations that you may need to make, and those you make using gamma. Okay. All right. So, how do we prove this? So, this is proven using what is called pigeonhole principle or Dirichlet's box principle, right. And so, here is, let us make some simplification for the proof. Okay. So, if we multiply A, alpha, beta by same integer n, the hypothesis and conclusion do not change. Right. So, we may assume A is actually contained in OK. We may assume that A is an integral ideal rather than a fractional ideal, and that is what we are going to do. Okay. All right. Now, what I am going to do is I am going to do the following. Right. So, what I am going to do is I am going to take m beta by alpha. Right now, I have not put any bound on m could be arbitrary, but it does not matter. So, this thing I can write as summation bi alpha I going from 1 to n, and these bi's are rational numbers. Okay. All right. So, what I will do then is so for each such m, let gamma m be an element of OK such that, so gamma m is an, I mean, these bi's, these are rational numbers, right. So, but they could be bigger than 1. I want these bi's to be smaller than 1. Well, that is not going to happen automatically. So, I am going to have to subtract something from it, such that m beta by alpha minus gamma m is equal to summation C I m, let me write it like this, alpha I going from 1 to n with 0 less than or equal to C I m less than 1. Okay. So, one can always do this, right. So, this this P m, which is equal to C 1 m and so on up to C n m, is in the unit cube, right. What is this unit cube? Well, this is x 1 up to x n in R to the n, such that 0 is less than or equal to x I is less than 1 for all I. This is the unit cube, the obvious thing. Now, what I am going to do is I am going to partition this unit cube. So, partition this let me write this unit cube as capital C, C into m minus 1. So, recall what is m minus 1, m minus 1 was n times C plus 1, sorry, yeah, maybe there are too many C's. So, let me write the cube by some different, so let me write it as delta. So, delta into this number of smaller cubes, right, of equal size, of size of side, each side will be 1 by n times C plus 1, right. So, if I can, you know, I can partition my bigger cube into, if it is a 3-dimensional thing, then I can partition it into 8 cubes of size each side half, or 27 cubes of each side 1 by 3 and so on. So, now my side is n times C plus 1. So, there will be n times C plus 1 to the n cubes, right. So, that is where my number m comes from. Okay. All right. So, so that is that. Now, now if I take, so okay, so now my m, so my m is an integer such that 0 is less than m is less than or equal to m, right. So, maybe it is more elegant to write it as 1 less than or equal. So, there are m plus 1 of these. So, there are P1 up to Pm numbers in this unit cube delta, right. Those are my, see, I have defined Pi's like this. Okay. So, now there are m minus 1 cubes and m plus 1 point, sorry, m points. So, 2 of these points must lie in the same small cube, right. So, 2 of these m points lie in the same small cube, right. So, let us say P m1 and P m2 lie in the same small cube. Okay, and let us say that m1 is bigger than m2. All right. So, what am I going to do then? I am just going to consider m1 minus m2, which is another positive integer, beta by alpha minus gamma m1 plus gamma m2. Okay. And so, so if you let m be m1 minus m2, gamma to be gamma m1 minus gamma m2, then it is easy to verify that height of m beta by alpha minus gamma, this is less than or equal to C plus 1 inverse, just by the fact of how things are, right, I mean, because of this. All right. So, if I, okay, maybe I will write it this way. So, this is summation C I m1 minus C I m2 alpha I, right. So, because mod of C I m1 minus C I m2, because they are in the small same small cube, this is less than or equal to 1 by n times C plus 1. Okay. So, that is how That is how we get the height is C plus 1 inverse, right, because you are adding n of these things, and so you have to have n in the denominator. All right, so fantastic. That's the main technical thing that we are going to use. Now we are ready to prove our theorem. If K is a number field, then the ideal class group of K is finite, right. So, what do? We do the following. So, here is a, well, again a lemma before we actually prove that. So, let epsilon be summation ei alpha I. So, epsilon and epsilon prime be summation ei prime alpha I. These are elements in, let us say, K. So, I want to relate height of epsilon epsilon prime with height of epsilon and height of epsilon prime. So, here is what the relation is. Then the height of product of these two things is C is less than or equal to C times height of epsilon prime. And remember, this C is the same C that we had before, and it is because of this lemma that that particular C is relevant. Okay. We could have proven the previous lemma with any choice of C. So, it was not necessary to take that particular C, we could have proven this with any choice of C, but we take that particular choice of C precisely because of this lemma. Okay. So, this is not hard. So, what you do is you take epsilon epsilon prime, height of this is same as height of summation ei prime of epsilon I, sorry, ei ej prime. So, that is what the product will be, right, which is less than or equal to summation I j mod of ei ej prime, right, height of alpha I alpha j, but that thing is bounded by C. So, this is less than or equal to C times summation I comma j ei ej prime, but this thing is precisely equal to the product of these heights, right. So, that is how the lemma is proved. All right. So, how do I use the lemma now? Right. Okay. So, back to the proof of the theorem. So, let A be any fractional non-zero fractional ideal and alpha in A be of minimal height, then then what we do is we take then we take M all right. I have to take beta as well, right. So, let me fix that. Take M and gamma such that height of M beta by alpha minus gamma is less than equal to C plus 1, right. So, that is what was given in that main technical lemma we proved. So, now what you do is you consider M beta minus gamma times alpha. So, remember gamma is in OK. So, this thing is in A. Okay. It's an element of A. What is height of this M beta minus gamma alpha? This is equal to height of alpha times m beta by alpha minus gamma, which is less than or equal to c times height of alpha, height of m beta by alpha minus gamma, right. But now this thing is less than or equal to c by c plus 1 times height of alpha, right, which is less than height of alpha, because c over c plus 1 is less than 1. But now we had chosen alpha to be something of minimal height, right, as alpha in a minus 0 was of minimal height, m beta minus alpha times gamma is equal to 0, right. What does this mean? This means that m times beta belongs to the ideal generated by alpha. Okay. But now beta was an arbitrary element, right. So, if you take so hence m factorial times beta is in the ideal generated by alpha for all beta inside A, which means that m factorial times A is contained in the ideal generated by alpha, right, which means that A1, if you define it to be to this way, is an integral ideal. But it also, but you see that alpha is contained in A. So, A by alpha is integral, sorry, yeah, I mean, okay, I do not want to write it this way, let me write it like, let me just write it like this. So, m factorial is contained in A1, right? I mean, just by the fact that that alpha belongs to A, which means that 1 belongs to A by alpha, and so A1, which is m factorial times A by alpha, contains m factorial, right. Okay. So, this means that m factorial OK is contained in A1 is contained in OK, right. So, this means that norm of A1 is at most m factorial to the power n, right, and this is independent, this is independent of A, right. On the other hand, notice that as A1 is m factorial by alpha times A, the class of A is same as the class of A1 in ideal class group of K, right. This means, so we have proven every ideal class contains an ideal, an integral ideal of norm less than or equal to m factorial to the n, and we are done, right. As there are only finitely many such ideals, CLK is finite. All right. So, this is one of the main theorems in this course, that the ideal class group is finite. Now, you see, how do you get the bound here, right. So, to get the bound, you first have to find m, and to find m you look here, right. So, you first have to find C, which is some integer. So, the smallest value that C can take is 1, and so the smallest value that m can take is 2n to the power n. So, even if you are in a quadratic extension, it will be 4 to the power 2, which is 16 plus 1, right. So, 17, and then you have to take its factorial, m factorial. So, 17 factorial, and then you take its square again. So, even for quadratic extensions, the bound will at least be equal to 17 factorial square, which is huge, right. So, it is not practical at all to compute ideal class groups this way. And so, our next task not immediately, but later on we will give a much better bound on the than this m factorial to the power n. This uses what is called geometry of numbers, and is mainly due to Minkowski, and that will be our next task. But next time we will just use finiteness of class group to prove a number of results about norm, and we will prove this lemma that we did not do 2 lectures ago. Okay. Thank you.